Hello guys, so we are going to continue the discussion with respect to deep learning. In our previous video, we have seen the high level overview, right? 1000 feet high level overview regarding forward propagation, backward propagation and all. Now we'll deep dive into backward propagation and we'll try to understand what is the main use and importance of it. Now, yet over here, this is a two-layered neural network because I have my hidden layer 1 and the output layer. Okay. And again, as I said that in a hidden layer, I can have any number of neurons and I can also add any number of hidden layers, right? So here what I've done is that I've taken this input layer and I'm giving 3 inputs, which based on my data set like this, x1, x2, x3. These inputs are basically my independent features. This is super important to understand, guys. These are my independent features, right? And this is my dependent feature. Okay, dependent. That basically means this value will change based on these inputs getting changed. Okay. Now here you can see that for solving this problem, I have taken an input layer which has 3 inputs, that is IQ, study hours and play hours. In the hidden layer, I've taken 2 neurons, right? And bias is also getting added over here. Next bias is also getting added. Here you can see this all inputs will be connected to all the hidden neurons also. And here you can see W1, W2, W3, W4, W5, W6. These are the weights that are getting initialized, right? And then from the hidden layer to the output layer, I'm connecting it with 2 lines, which is having W7 and W8 as the weight initialized. Okay. And this is basically my output layer. Now you may be thinking why I've used just one output neuron over here, right? This is very important to understand. Why can't I add 2? Understand the type of problem statement that we are solving right now. It is with respect to output 0 or 1. So this particular neuron is going to give the output as 0 or 1. So that is the reason I'm just used 1. Let's say if there is a multi-class classification problem, suppose let's say there are 3 outputs over here, I can basically use 2 neurons, right? So it can either give 0, 1, 2, like that kind of outputs, right? So with respect to that, I can give 2 or 3, right? Based on the multi-class classification, I can add that many number of neurons in the output layer. Now this is clear. I hope everybody's clear with the forward propagation. As I said, in the forward propagation, what we do, we take this inputs multiplied by the weights and then we add a bias and then we apply an activation function. Now, since I have used 2 neurons over here, now the matrix multiplication that is going to happen will have a shape of 3 cross 2. Why? Because I have 3 input layers and 2 hidden layers. So x1 w1, x1 w2, x2 w3, x2 w4 will get multiplied and it will keep on getting added, right? x3 w5, x3 w6. So I'm going to get this kind of neurons. That basically means from here I'm going to get x1, x2, x3, right? And from here I'm basically going to get 2 layers, w1, w2, w3, w4, something like this. Let me just write it down again. So here it is. So let's consider this one. So I have 3 neurons. So here what I will be getting, 3 inputs. So here I'll be having x1, x2, x3, right? And in the other side, the other matrix will have w1, w2, w3, w4, w5, w6. Okay. So something like this, right? So if I probably consider this, now see, with respect to this x1, I'll be multiplying with w1, w2, then x2 will get multiplied to w3 and w4 and it will get added obviously, and x3 will get multiplied with w5 and w6. So in short, if I probably combine these 2 matrices, I'm going to get a final shape of 3 cross 2, right? 3 cross 2 matrix. So just to understand this, just understand in a simpler way, we are just multiplying 2 matrices, okay? Then what we do, we apply an activation function, we go ahead, we find out the output, and finally we go to the output layer. Then after this, what we do, we calculate a loss function. Now, since this is a binary classification problem, and there are multiple different types of loss function. Some of the loss function, I'll just like to mention it over here so that, and we'll discuss about this loss function. For regression and for classification, we have different loss function, okay? And for regression, let's say I have something called as mean squared error. For regression, I have something called as mean absolute error. Third one that I can basically use is something called as Huber loss, right? Similarly, in classification, I have different loss function like binary cross entropy, and then I also have something called as categorical cross entropy. We'll discuss about this, don't worry, okay? Categorical cross entropy. We'll discuss about all these loss function in depth in the upcoming videos. Okay. So in short, these all are some formulas which will basically, if I really want to use a simple loss function, I will just say y minus y hat whole square. That basically means whatever is the predicted output, whatever output that I'm getting from here, that will basically means the difference between the real output will be calculated. And our main aim is to reduce the loss function. Let's say if we get a very big loss function, then what we do? We have to update all these weights. And updation of the weights usually happens in the backward propagation. Okay, so this backward propagation will happen. Okay, and how the weights updation formula will be there, I will talk about it. Okay, so backward propagation will happen, wherein we will focus on subtracting this weights and updating it. Okay, now this is the idea, and this is what we discussed in the last class also, right? Now let me go ahead and let me show you with respect to the weight updation formula. This is super important. Okay, weight updation formula. Now in the weight updation formula, here you can see that when I am doing the backward propagation from here, from the loss, I am going to do the backward propagation. The first weight that I will be probably getting is something called as W7 and then W8. Okay. Now this W7 will get updated something like this. So W7 is equal to, and I would just like to write W7 new, because this will be the new weight, is equal to W7 old minus this notation. I will explain you what exactly this notation is. And then along with this, we will try to take derivative of loss, whatever loss I'm getting. Okay, derivative of loss with respect to derivative of W7 old. Okay. Now this is super important to understand what this derivative of loss with respect to derivative of W7 old is. This in short is that we are trying to calculate the slope of the graph which we plot with respect to the weights and the loss function. Usually with respect to different loss that we have, like MSE, MAE, or binary cross entropy and all, right, we usually get something called as gradient descent. Okay, so this is what a gradient descent is. This kind of curve usually is created by a gradient descent. And if you know machine learning, if you just know linear regression, or if you have seen my video with respect to linear regression, so here you'll be able to see that this is the global minima. This is where we have to come, or we have to arrive. Our entire weight should come to this particular location, because here the slope is exactly 0. And when the slope is exactly 0 over here, that basically means we don't need to update the weights. Okay. So derivative of loss with respect to derivative of W7, let's say it is this specific point. So when I do derivative of loss, in short, I'm just trying to find out the slope. And I'm saying that whether this is a positive slope or negative slope. Okay. And by this, we try to update this specific weight. Okay. And this is the formula. For W7 new, this will be the formula. For W8 new, this will be W8 old minus this value with respect to derivative of loss with respect to derivative of W8 old. I will talk about this. What is this parameter also? Okay. So this parameter is basically called as learning rate. Okay. I will talk about the importance of learning rate also. Okay. In this video only, I'll be talking about. Now, why this formula will work. Okay. And like this, we have all the weights, and probably if I really want to write a generic way of writing, it is nothing but W new is equal to W old minus the learning rate of derivative of loss with respect to derivative of W old. So this entirely is my weight updation formula. This entirely is my weight updation formula. So this is my weight updation formula. Okay. So it is very simple. Now, why this formula will definitely work? Let us understand this. Okay. Let's say I have this gradient descent, because with the help of this loss function, with the help of this whatever loss function we are trying to use, we will be getting this kind of gradient descent most of the time. And we'll try to understand whether there will be chances of any local minima or not as we go ahead. But just understand the importance of this loss function is that that we will be almost getting this kind of gradient descent when we plot with respect to weights and the loss function. Okay, so let me just go and draw this. So this will be my gradient descent, let's say. Okay, now my main aim is to basically update all these weights with the help of back propagation. Whenever we get this kind of loss function, if we want to minimize this loss function, we use a concept called as optimizer. And this is what an optimizer will do. This optimizer is called as a gradient descent optimizer. And there are different types of optimizers also, which we are going to discuss. Let's consider a simple gradient descent optimizer. Okay, gradient descent optimizer, and like this we'll have many optimizers. The optimizer's role, again let me repeat it, what are the optimizer's role? This optimizer's role, I'm going to write each and everything, so just be patient and just try to understand these things. Okay, so what are the optimizer's role? Optimizer role is to reduce the loss value. Super important. Okay, that is our main aim, and we will be only able to reduce this loss value. We'll be able to reduce this loss value only by updating these weights, because in the backward propagation we are updating all these weights. Now let's see how the weight updation will happen. Now you know that our aim is basically to come in this. Why? I'll talk about it. Why? Let's say this is my initial weights, and with respect to this weight, let's say I've got this loss function. Now this is super important. Okay, I have used the formula, which is W new is equal to W old minus learning rate of derivative of loss with respect to derivative of W old. Whenever I say derivative of W old, right, I need to update this weight. That basically means I am trying to find out a tangent over here, or I'm trying to find out the slope with respect to this line. Okay, now the first thing is that with respect to the slope basically means with the unit movement in the x-axis, what is the unit movement in the y-axis? That is what is the slope that we really need to compute. Okay, now the first thing is that we need to understand whether this slope is positive or negative, and the best way to understand this is that see the right side of the line. The right side of the line is pointing downwards. Whenever this right side of the line is pointing downwards, understand again what I'm repeating it. Whenever the right side of the line is pointing downwards, okay, then what kind of slope we will be getting? Just think over it. We will be getting a negative slope, and this can be proved mathematically also. You just go and see. Right? If it is pointing downwards, it is basically saying it as a negative slope. That basically means W and loss are inversely proportional, right? So if I, with respect to this, whenever I try to calculate the derivative of loss with respect to this particular value of weight, you'll be seeing that I'm getting a negative slope. Negative slope basically means negative value. Now my W new will be nothing but W old minus learning rate with some negative into negative value, right? So that basically means now what is basically happening, and this is basically 0, and as we go ahead and increase, W is increasing in this direction. Now this is a negative value, right? So if I try to add this up, W old plus, it will be learning rate with a positive value now, right? So here we are increasing the W value. So finally you will be seeing W new will be greater than W old, right? Because negative into negative is positive. So what we are doing over here, we are probably trying to increase the weight. And understand, we need to come to this location. Why? Because in this location, this point is basically called as global minima. Super important. Okay. This point is basically called as global minima. Okay. And our main aim is to come over here. And you can see with the help of this weight updation formula, we are doing the same thing, right? First of all, with this W, I got it a negative slope. So if I'm getting a negative slope, that basically means I have to increase the weights to this particular point, and that is basically happening. The W new value that we are going to get is going to increase. So this is definitely going to work. Let's say with respect to the other scenario, let's say if the W value is over here, then with respect to this, I'm getting the loss value over here. Now let's go and calculate the slope over here also. So here, let's say the slope is this one. Okay. Now in this case, you can see the right side of the line is pointing upwards. Okay, let me write it down much more in a better way. Let's use a green color. So this is my slope. Now when I try to calculate its slope, the right side of the line is pointing upwards. When it is pointing upwards, this becomes a positive slope. Now when I have a positive slope, that basically means I have to decrease my W value to come to this, right? So if I try to apply the same formula, what will happen? W new is equal to W old minus learning rate of derivative of loss. Derivative of loss is derivative of W old is nothing but this is a positive value. So minus into positive is positive. So W old minus learning rate with some positive value. In this scenario, the W new will be less than W old. Do you agree? Because we are reducing something, will obviously be less than this one, right? We are reducing something. So based on this two condition, we are able to get this, right? And at the end of the day, my main aim is to come to this point, right? So definitely this weight updation formula will work. Okay, this is super important. Then what will happen? Let's say the next point, let's talk about this one, the learning rate. This is super important, learning rate. What is the importance of learning rate? Let's say if I initialize this learning rate to a smaller value, let's say the smaller value is 0.001, and usually we initialize a smaller value. Then what will happen? Let's say for this scenario, I will just add this W old by a smaller value. So my next point, what will happen? The weight will get updated to here, right? And with respect to this, my new loss function will come over here. So this learning rate decides the step size towards this global minima, how fast it really want to converge, right? Because it will be a continuously iteration process, right? We need to continuously update the weights because we are doing the backward propagation. Then again, we'll do the forward propagation like that, right? What happens if we initialize this to a large value? This is also very super important to understand. Then what will happen from this point? You'll see that we'll not be having a small step size. We will be jumping here and there, right? Because the value is quite big. And sometime it may happen is that we may go outside this gradient descent and it will never converge. So in this scenario, it may never converge. So it is always a good practice that we take this learning rate to a small value. Super important, right? So I hope you got an idea about what we're discussing over here. At the end of the day, we need to come to this global minima. So when the optimizer will understand that, okay, finally the weight updation is done. See, once the W comes over here, right? Over here, when we try to calculate the slope will be 0. So this entire value will be 0, right? When this value will be 0, this into this will be 0. So W new is equal to W old. So when W reaches, so I'm going to put a very important point. When W reaches global minima, my W new is equal to W old. That basically means I have reached my global minima. I don't have to update more weights and my loss function will also keep on reducing. Because over here you can see the loss is near to 0, right? If we go downwards, over here also the loss is decreasing. Initially the loss was high. And when we are coming downwards, it is becoming 0, right? So this was the idea about gradient descent optimizer. Similarly, there are many types of optimizers which we are going to learn. And we'll try to understand what are the importance of each and every optimizers as we go ahead. But I hope you got a clear idea about the weight updation formula and what exactly is happening in the backward propagation. But still, we just discussed about W7 and W8. We also need to know that how does W1, W2, W3, W4, W5 weights will also get updated, because this W1 is dependent on W7 also. I mean, this W7 is also dependent on W1. W8 is also dependent on W2 because this is connected. And that is what we are going to learn in the next video, which is called a chain rule of derivative, right? And we'll try to understand how chain rule of derivative is useful in calculating the weights of W1 and all, right?